So let's describe numerical solutions of second order differential equations, and for this let's first recall the way the problem is presented to us. So we are given an initial value problem involving a second order differential equation, which is described over here. The second derivative of the dependent variable y is known in terms of some capital F, some function which depends on time, it depends on y, and it depends on the first derivative of y. So this capital F is known, and so that's the given differential equation. It can be of an arbitrary complexity. And we're given the initial conditions. We're given two initial conditions for a second order ODE. We're given the value of the function, and we're given the rate of change of the function as y0 prime at time t equal to t0. So that defines the initial value problem, and so we want to solve this initial value problem numerically. And so the step is that we want to cast it as a problem that we already know how to solve. And so there is a very useful step, which is to recast this problem. We want to rewrite it such that it is seen as a system of coupled first order ordinary differential equations. And so this is actually very straightforward to achieve. So we define vector y. Originally y was a scalar quantity, so we are now introducing a vector valued y, which has two components, y capital 1 sub 1 subscript 1 and capital Y subscript 2. And so we need to define what capital Y1 and capital Y2 are. And so they are simply y itself. Y1 is equal to y, and y2 is the derivative of y. So those are the equations that we have written over here. Capital Y1 is equal to little y, and capital Y2 is the time derivative of y. And so given these two, it follows that if I take the derivative of this first function, capital Y, y1 prime, that would be y prime. But we have already given a name to y prime. We have called y prime equals y2. And so this equation therefore follows from our definition that y1 prime is equal to y2. This is a first order differential equation relating the first component of y1 to the second component of y. All right? And so if we try to write this more generally, if we say what is the rate of change of the complete vector y, then y prime is y1 prime and y2 prime, the rates of change of the two components. Y1 prime, we have just seen up here, is equal to y2, so we substitute that here. And what is y2 prime? Well, y2 prime by definition, well, y2 as we have noticed here is equal to y prime, and so one more prime on that would give us y double prime, is the second derivative of y with respect to time. But the differential equation defines that for us. Y double prime is given by capital F, which depends on t, y, and y prime, so we're calling this y1 and y2. And so now what we have, if we simply define this vector as a vector capital F, which depends on t, and the vector capital Y with components capital F1 and capital F2, what we have is a system. The second order differential equation has been recast as a system of first order differential equations, two first order differential equations to be precise. And this method is general, so that if we are given nth order ODE, we can write it as a system of n first order ODEs. So this idea generalizes, and so once we have rewritten the system in the form of a system of first order differential equations, we can apply numerical methods that we have learned for solving first order differential equation to solve the higher order problem. So let's proceed with that. And so we are going to apply numerical methods for first order ODE, which we had originally written for a scalar equation. We are simply going to apply it in vector form for the system of equations that we have. And so we have already shown that the equations can be written in terms of a system. It is very straightforward to see that the initial conditions can also be written so that the initial condition for the vector capital Y is simply the elements of the initial conditions that were given before. Y0 and y0 prime are known numbers. They are the elements, y1, capital Y1 and capital Y2, elements of the initial condition for the vector Y. So we have the differential equation in form of a system, and we have the initial condition in the form of a system. And so we now apply the numerical method to each component of the system. And so we can write, for example, first order Euler method can be written in this way, that at time level n plus 1 we obtain the solution by taking the solution at time level n, and to it we add delta t times the differential equation right hand side evaluated at time tn at the dependent variable y sub n. And this is the first order accurate method. If we desire higher order accuracy, better accuracy than this, which is very easy to obtain by using the second order Euler method or predictor corrector approach, where we take a first step, we compute a predicted value of y, yn plus 1 p, using the same step idea, the first order idea that we had mentioned, and we use this to improve the prediction at the level n plus 1. So we say yn plus 1 is equal to yn plus delta t times 1/2. So this is the value of the right hand side at 2 times at time tn, when we know capital Y there, and at time tn plus delta t, we can call this tn plus 1. The value of y is not known, but we have a prediction for it. We have an estimate for it, which we can use. So together with that, we can have 1/2 is arithmetic average, and that then allows us to have a prediction for yn plus 1. And since we know y is 0, we can start this calculation from the initial condition and just take the steps and go to the final time that is of interest, and then look at how the method is behaving, and analysis of errors, convergence of the method, and so on can be analyzed in exactly the same way as we have described for the first order equations.